our distinguished colleague, Professor Mutifi Temple, or I don't know who's teaching you physics and mechanics, did that already. If you are pulling, I don't know, a cart or something, you have a power there, right? This direction. So here, I don't know if you are pulling something. Okay, assume you are pulling this in this direction. So this will have components, right? You know how to evaluate these components. If this is theta here, you remember? If this is let's say a magnitude of a vector A. So what will be this? You have an x and y component. You remember that?
The vertical will be sine theta, a sine theta, and the horizontal will be a cos theta.
Okay, exactly. So this is A times sine theta, and this is
No, the opposite.
a cosine, sorry. This is cosine theta, and this is A. Now I think it's clear where this A sine theta comes from. Okay, so this is how we just find out the vertical and the now another thing here, what if you are to evaluate the area of the triangle? Guys, do you have questions there? Question? It's okay. So what if I'm asking you, you see here using this product, you can find the area spanned by two vectors of the parallelogram that's spanning this, or that these vectors are spanning. If I'm asking you for the area of the triangle, of this triangle, what is the area of the triangle?
Half A B sine C.
It's half, yeah? Obviously it's half, yeah? So here I'll just write them as in informal notes. Note that the area of the parallelogram spanned by the vectors, sorry, as a vector, vector A and vector B, is, if we just say this is A, and let me just put it here to distinguish it as something similar to the shape of a parallelogram, then A of this parallelogram is equal to the magnitude of A cross B, and which is ultimately equal, of course, to the magnitude of A times magnitude of B times sine of theta. Spanned by the vectors A and B. What is this here? This is not. Okay, so guys online, we cannot see. Huh? You cannot see. Yeah, it's okay now. Okay. Okay, so the area of the parallelogram, this parallelogram, is nothing else than the magnitude of the cross product. So if you are given two vectors, you want to evaluate the area of the parallelogram, then you evaluate the cross product. Then the outcome of the cross product, you just calculate its magnitude. Now, obviously, let me just squeeze it here somehow. The area of the triangle here, I just write it here, is equal 1/2 of the area of the parallelogram. Okay. So if you are to evaluate the area of the triangle spanned by two vectors, Then you evaluate, go all the way, evaluate the cross product. I will show you how to evaluate it. Then take just the magnitude of this outcome and divide it by 2. Okay? Area of the parallelogram is the magnitude of the cross product, area of the triangle is half of that. Because this is one of the features of parallelogram is that the diagonal, it will split it into 2 equal triangles. Okay. So honestly, there are lots of applications in real life of this. One of them is the magnitude, is the so-called the momentum, and the force if you are just using you know some sorry, some tools, yeah. Like, I don't know what's the name of English of it. Really, I know it in German, but not in English. This one,
Yes.
Gabel. Okay, so this is the force. This is the magnitude. So the momentum is just the application of this. So there are lots of applications in physics for this particular. It's just one of the applications. Now let me just introduce something. Let us agree on something now. How to evaluate the cross product? So as far as I know, cross product is usually related to 3-dimensional vectors. Could be also for 2. I can't imagine. So for 3-dimensional vectors. Anyway, I want you just to agree with me on the following, and I hope that it's fine for everyone. I know that in some countries they don't use that, others they use different methods. It's fine to me with which method you are using, but I will just introduce this, and I hope you will be using that. Okay, now cross product in this. Okay, now what I'm going to do, we will agree on the following. This is the x-axis, this is the y-axis, and this is the z-axis. I'm going to define the unit vector here as a vector that is I. Maybe at the beginning we will use a hat on top of it. Later we will just, this is J and this is K. So I told you in the previous lecture that in some literature we refer to this as E in the power x. This means the unit vector in the x direction. This means the unit vector in the y direction. This means the unit vector in the j direction. And remember that I coordinates as it's stated here is equal to the x coordinate is 1, 0, 0, right? So it's here located. This is 1, this is 1, this is 1. Okay. Yj coordinate, you remember these vectors 1, 0, 0, 1, and 0, and k is just the vector 0, 0, and 1. Okay. And we saw that these 3 vectors, they are in literature, it's used very, very often as x unit vector, E sub x, E sub y, E sub z, or different. Let's agree on I is this vector, unit vector in x direction. J unit vector in Y direction and K is unit vector in Z direction. Is it difficult for anyone that's using this notation? So instead, for instance, if I have the vector, let's say A equals 1, 3, and 2. Okay, then in this notation, A is equal to I plus 3J plus 2K. Okay, I'm going to just omit these hats later, but it is IJK that we will ultimately be using. Okay, so this is just the same vector. Yeah, this is just the same vector. You interpret it as this vector has 1 unit in the x direction, 3 units in the y direction, and 2 units in the z direction. Okay, everyone agrees on this notation?
Yeah.
No need to for screenshot because you know what. Okay, so it's already on island. It's already on island. Okay. Now finish. Okay, you're welcome. Okay. Now let's see some properties, some nice properties of properties of these unit vectors. I, J, and K. Okay. Now, obviously, if I have any two vectors, if I multiply as dot product, okay, I dot I, what do I get? How do I multiply? I is just 1. So here I have a second.
0, 0.
What you will get there?
1, 0, 0.
Sorry? What do you get? 1, 0, 0 times 1, 0, 0. You just multiply the x coordinates, 1 with 1, add it to 0, another 0, right? No? So what do I get here? Let's just do it. 1, 0, 0, dot 1, 0, 0. Let's apply the rule here. 1 times 1 plus 0 plus 0, right? So it's 1, right? Correct? The same applies to J and K, because you will be having, in one case, the middle, it will be 1, and the other one, it will be the last coordinate. So in this case, this is also equal to 1. Okay. However, the cross product I cross I, what do I get? What is sign of 0? Sign of 0 is 0. So you get 0. The same applies to J cross J, and the same applies to K cross K. So it's 0. Okay, now comes to a mixture, you need a little bit to be careful, okay? Now I times J, I times J. So I don't know here whether you can just follow what is the right hand rule. What does it say? It says you go from I to J, and then, so if you like here, I is pointing. Okay, so the plane that goes from I to J is this plane, and this is the perpendicular line to it in the direction of K. I hope it's clear for everyone that if I just evaluate I cross J, then I will be getting K. Okay, so it means the vector that is perpendicular to the plane using the right hand rule. Okay. Now, since this is a two-dimensional, you can think about it. Yeah, right hand rule. So you have so everyone can try to simulate it for him or herself. Okay, so imagine that you have these two fingers in one plane, and this is the one perpendicular plate, which is in this case K. And notice that if I have any one of them in the other direction, then it will be negative. So that means here J cross I is going to be negative K. It will be actually the vector that goes in this direction with one unit, so in the negative direction. Okay, now similarly, any two other vectors like J cross I, negative J cross I, it's going to give me also it's going to give me K. And I have here another interesting J cross K. It's going to give me negative, of course. So it's going to give me I. And it will be, if I just negate J here, it or K, negative K cross J. Okay. Because K cross J, it will be in the other direction, but if I negate it, it will be then in the same direction, because they are just opposite to each other. And similarly, if I have here K and I have K cross I, and this is equal to J, and this is equal to negative I cross K. So since we have here the three unit vectors are perpendicular to each other, they have these relationships. Okay, so
Professor, could we see some examples with the negative?
sorry.
Can we see some examples with the negatives?
This is just the right hand rule. It's I hope you understand the necessity of the right hand rule is just to rule out which direction you start with. Okay, so the right hand rule you have you can Google it, and then you label one vector. This is the starting vector. This one is the B, and then you have these on one plane. So maybe with the finger, it doesn't look like it's in one plane. And then in this case, this will be this direction. Now imagine if you have one is the opposite of the other, that means you will be just in the other direction. This is the meaning of the negative.
But even in the other direction, it's still perpendicular, right?
It's perpendicular, but it is in other direction, right? So I was just saying that we're using the right hand rule to rule out any ambiguity of which direction, because you have two options, which one I take. Okay. So this is the meaning of the right hand rule. Now notice that if I take any one negative, then and what we do here, I take a negative and I then switch the order, then I'm there. It's just like I'm just doing two rotations, then I'm at the same position. Okay, so that means here, for instance, I cross K is going to give me what? according to this rule,
Okay,
negative J, yeah? Negative J. Okay? So this what this saying is simply if I negate someone, I take the opposite direction and I apply this product, I'm at the same position. Just think about it. You can Google this right hand rule and see how to place the fingers, and it's a little bit difficult to demonstrate. You need you see maybe I have here, even though it's two-dimensional. So you see maybe here this graphic. So these two here are on one plane, and here I don't know how this is a little bit. So this vector, this is
That's supposed to be like on the same.
the same plane. So this here, this shaded area, it means it's on the same plane. It's just like this is this direction, while this one, see, it's perpendicular to this. I hope you can it's perpendicular to this plane, and the other one, it's perpendicular from the other side. So this is the meaning of negative.
Professor, but what if both the vectors are negative?
Sorry?
What if both the vectors are negative? The both which are on the plane, what if they're both negative?
What if both are negative?
Both are negative, yeah. Then is the final one also going to be negative, or is it going to be positive?
It's going to be. So this is actually a good question. You mean here I and K?
Yeah.
Yeah, think about it until the break. After the break, you just take the two in the negative direction and then see what you get. Okay.
Okay.
I assume it will be positive. I assume
it will be positive because
Yeah.
it's still perpendicular like
Yeah.
this.
Of course, this in this case it depends which one to the right, which one to the left. Okay, so let's take a break and then continue. Okay, after the break, we will focus on a very important thing, which is evaluating the determinants.
B is still going to